Hi, I'm Laalitya Acharya, and this is Electra, generating energy from a multitude of sources, including piezoelectric materials, photovoltaic materials, and low-flow, low-head hydropower. So my grandfather used to tell me that when he was younger, he and his siblings would study around a dangerous kerosene lamp. Now, this was in 1940, but for over 2.5 billion people across the globe, light poverty, which is having little to no access to energy, remains a reality. And those who do have access to energy are relying heavily on conventional energy sources, aka fossil fuels, which is leading to increased pollution and other negative environmental impacts, and the possibility of running out of fuel. The current renewable energy sources are not up to par either. They have huge initial investments, long return on investments, negative environmental impacts, and can lead to human displacement, for example, for dam construction. We need to find a cheap, renewable, clean energy source fast. I decided to undertake this journey, and as I started researching, an idea came to me. What if I could combine multiple sources of energy into one device for application in many environments and for an affordable and clean resource as well? I decided to use vehicular motion, solar power, and hydropower as my main energy sources. I decided to use piezoelectric materials to generate energy from the vehicular motion, photovoltaic materials to generate energy from solar power, and a low-flow, low-head water turbine to generate energy from the hydropower. I then designed some design success criteria as well to ensure and test whether or not my device will actually work, and to have something to measure up the standards. So I started off by testing my piezos. I tested 4 different piezos and selected the final one, a polyvinyl film with and without mass to generate energy, as it created a variety of vibrations and had a high output of 1000 millivolts of energy and about 6 milliamps of current. After I selected this piezo, I put 2 blocks of wood together with the piezos in between to mimic a road. But as I started testing this component of my final device, I realized that there was a problem. As I pressed my piezos, I realized that it was not at all consistent and was quite varied. What this meant was that the results I was getting was varied as well. So I had to create this reciprocating motion machine using Lego EV3 Mindstorms. What this did is that it consistently pressed my piezos so that the results I was getting were very consistent and had a low amount of variability. I then moved on to testing my hydropower or water turbines. But before I could do that, I had to create a flow channel and a flow diversion assembly, as nearby universities did not have a flow channel that I could use. I used a plastic container, a garden manifold, and garden hoses to do this. I used the plastic container and put in holes for the manifold. Then I could lead a certain amount of water from the manifold away, so that only the remaining would actually be impacting the turbine. For example, if I opened all 4 of the manifolds and then led 2 of them out with a hose, only 50% flow would actually be impacting the turbine. I calculated my flows using Manning's equation, using an Arduino Hall effect sensor, and using the percentage method as well. When I finally tested my flow channel, it could have between 2.1 gallons per minute to 6 gallons per minute of flow. Now I could actually create my turbines. I designed 3 different turbines, turbine A, B, and C, and selected turbine C as it had the highest RPM of 122 rotations per minute. Then I moved on to creating a turbine assembly. I tried a direct transmission and a belt transmission for the movement of energy from my turbine to my generator. But this did not work and had a very low energy output. But a 4.5 to 1 gear ratio did, as it increased my energy output tremendously. By selecting this turbine and this turbine assembly, I could generate between 5.1 volts to 11.2 volts, and my current range from 1.23 milliamps to 8.4 milliamps. Then I moved on to testing my solar panels. I tested my solar panels on sunny and cloudy days to ensure that I had a quite broad variety of results, so that no matter what the exact weather was in the location where I could implement this, there would always be some sort of energy coming. So with this, my device was able to generate about 18.3 volts to 41.1 volts and 118 milliamps to 216 milliamps. Now I moved on to putting all these components together into one final device. My piezos on top with the solar panels next to them on my road, and below that having my water turbine to generate energy from a river if the device was implemented on a bridge, or from the stormwater drains if it was just implemented onto a road. My final device was generating between 33.8 volts to 51.8 volts. My current ranged from 118 milliamps to 216 milliamps. This meant that my wattage ranged from 5 watts of energy to 11 watts of energy. So this is a good innovation, but it is applying it that will truly make it better. I did a case study on Puerto Rico. Puerto Rico is currently in a major energy crisis due to the recent natural calamities that have occurred. Puerto Rico needs a sustainable, affordable, and clean energy resource right now. So I did a case study, and I found that Puerto Rico has high sun hours, high water flow, and high traffic throughout the entire year. What this means is that my device could be implemented in Puerto Rico to have its own nanogrid for emergency supply energy, or be feeding directly into the main grid for a larger scale supply. I'm actually working with the Red Cross in Puerto Rico currently to help bring this device to life, and I've sent a smaller version of Electra already on its way to generate energy. Because if we can even get one more hospital running or provide refrigeration for one more family, it can truly be worth it. But I also did a case study closer to home. I worked with local engineers and did a case study on the Brent Spence and Daniel Carter Bridge in my hometown of Cincinnati. The Daniel Carter and Brent Spence Bridge have an average traffic flow of 97,000 to 150,000 cars per day. Nearing Cincinnati, the Ohio River has a flow of 163 kilocubic feet per second. And in Cincinnati, the average sun hours, based on previous 8 years of data, has about 4.2 kilowatt hours of sunlight per day. This means that Cincinnati is a perfect location to help implement my device. And because of all the factors and multiple sources that my device uses, even if one component does not work due to an environmental factor, the location will still have energy. My goal is to work with local engineers to implement this in my hometown Cincinnati so that we can provide energy for libraries, restaurants, homes, and maybe one day entire cities and the globe. I hope that you too will join me on this journey of 1,000 steps of changing the world, simply 1 watt at a time. Thank you.